Hello, hello. My name is Natasha Selam, and I'm the head of AI research here at MindsDB. Thank you so much for joining us today. Accompanying me today is my talented colleague, George, who is both an engineer and an ML researcher. And today, we're very excited to be talking to you about our new feature we've been hard at work developing. Today, we'll give you a sneak preview of JSON AI, a declarative syntax, in fact, that we've developed to help users optimize their machine learning pipelines in a transparent, controllable, and customizable way. So the goal of today's talk will be first to highlight what MindsDB is, then discuss Lightwood, our ML core that allows you to deploy frameworks and train your own custom models, and then finally get to JSON AI, how you can control and customize elements of the pipeline to suit your data needs. Now, at the very end of this talk, we'll have a short question and answering session where we'll try to get through all of your questions. But in the midst of the talk, feel free to ping the chat or ideally the questions of anything that you have, and we'll try to answer live. So with that, let's first begin with why MindsDB is interested in this problem. And it turns out it's because ML ops, or ML operations, is non-trivial to be able to do. And in fact, it turns out in a recent study as of 2021, surveying small startups to Fortune 500s alike, more than half of companies have taken over a month to maybe even a year to deploy a single ML model into practice. And there's many different reasons as to why this is. The key and crucial element is that integrating with the complex ML pipelines is non-trivial. You need a way to be able to process your data, represent it in an appropriate form for a model to take, all the necessary steps to build robust predictors, and then bring it back to your application. So a key note to identify why this might be a problem is that there is a gap between how we treat and process our data versus the ML frameworks that currently exist to make these powerful models simple to access. In the following figure that I have here, we're looking at a timeline to look at the history of databases, a tried and trusted solution for how data is managed and stored, versus machine learning's history. Now, both fields have had tremendous progress and grand innovations to be able to access the complex forms that models can take and data can take. But only in the last 5 to 6 years have we seen a big push for democratized machine learning. And by that, I mean for example, Python packages like PyTorch and TensorFlow, among many others, that make deploying these very powerful algorithms simple and effective to use. Now, that gap exists between how we process and treat data, the core tenet of machine learning, to be able to then build a productive and robust model, and then bring it back to the application. So, in fact, when we study to see what goes on with companies, nearly half of them actually claim that integration challenges are rate limiting toward building models into production. And in fact, these challenges occur with the different myriad languages required to be able to process your data, bring it to your application, and all the requirements needed for establishing models. Now, looking at the life cycle of a data science and a machine learning project, a poll has identified that there are 3 key elements that we're looking for to be able to automate and make this process robust. The key 3 steps that non-technical users to experts like are: the first is data pre-processing, taking your raw data, being able to understand something about the statistical distributions, being able to process and clean the variety of outliers that can occur from data as it's a real world living thing, and preparing it for a model. The next step is feature engineering, transforming that data into something that a model can actually intake and process, and getting the most information out of it so that you can build robust predictors. And then finally, there's model building and training, which is deploying a variety of algorithms, identifying how best to train them for the target of interest, which is the quality that you want to predict. And then finally, being able to demonstrate that this is in fact the right model and deploying it into your application. Now, with that in mind, MindsDB identified 3 main pain points of the data science ML cycle, and we want to be able to have robust answers to all 3. The first, how can we simplify ML ops? so that users can interface with models in the same way that they interface with data in a database. Querying is a very natural, intuitive thing that we access and understand our data. But to allow that capability to be able to do this for predictors allows you to ask very natural questions of your data to get predictive insights. Secondly, how do we integrate with the state of the art in the ML frameworks? Every couple of months, a very, very powerful model is developed, and we want to be able to not only do tried and true methods, but to also integrate with useful things that are currently out there that could leverage really strong insights. And then finally, we want to be able to customize ML ops pipelines. We believe that users know their data best and that domain experts know how to prepare their functions appropriately to get the most insight from their predictors. And so we want to talk about how we might be able to customize ML ops pipelines. And so the goal of this talk is threefold. First, I'll turn it over to George, and he'll discuss what MindsDB actually is, and in fact, how we treat models as abstractions or AI tables to allow you to query them as if they were any data set within your database. Next, we talk about how we integrate state-of-the-art ML frameworks with simplicity. So I'll be discussing our package Lightwood. And in specific, Lightwood is a flexible AutoML framework that allows you to abstract data pre-processing, feature engineering, and model building for a reproducible and robust framework. And lastly, and not least, we will discuss our declarative syntax that allows you to customize the internals of machine learning models. As you know, with machine learning models, there are many different specifications to ensure that you get the most predictive bang for your buck when you build your data. And so being able to change these shouldn't be as difficult as going to massive code bases and editing source code. It should be as simple as changing a few flags or even importing your own custom modules. And we'll discuss a sneak peek as to how that might occur. And with that, I'll turn it over to George.
All right. Hello, guys. So this talk is mainly focused around Lightwood, right? Which is this, you could call it a declarative automatic machine learning library, which is just a fancy way of saying that as a developer or a researcher, you can use it to quickly create predictive models based on your data and customize those models. However, Lightwood is often used in the context of MindsDB, even though it's a tool that stands on its own. So I think it's fair that we first talk about MindsDB, since if you are interested in Lightwood, you are likely going to be interested in MindsDB and vice versa. So what's MindsDB? Well, broadly speaking, it's this platform to help you bring machine learning models into production. We are currently designing it with Lightwood in mind, with our own automatic machine learning library, but really you can bring any code, any machine learning code into production with this. You just need to adhere to this really simple interface where you define a learn function and a predict function. And then in principle, you'll be getting all of the power of MindsDB behind that, right? That power essentially being that MindsDB helps you simplify ML ops. So the, let's say, DevOps infrastructure side of machine learning. So how does that work? Well, conventional approaches treat machine learning as somewhat decoupled from both the database and the applications using said database and said data. Maybe it's a separate service that's maintained by your data science team that you call via some API. Maybe it's an awkward module that sits in your application and you run it on a separate thread or as part of a separate process, and like there is just a guy that knows how to deal with it and you don't have to ever touch it when deploying. And based on the slides Natasha was presenting, maybe it's just something that like the PMs and the marketing people talk about, and in principle it yields good results, but like for the last 2 years it's never actually been used because it doesn't quite work when you try to productionize it in any way. I know that was the case in a lot of companies, and so they kind of gave up on introducing machine learning solutions because they weren't critical and it was just very annoying to integrate them with the existing applications. And this makes, like, this way that people have right now, production as machine learning, really makes very little sense from the perspective of an application developer. Because machine learning, if you think about it, should behave exactly like a database. After all, you're basically using both of those for the same thing. You are giving your application data, which hopefully reflects reality. So you may ask your database something like, okay, what's the email for a given user? But currently, you can't ask a question like, what's the risk that this user will churn, that he will drop from our service? Or what's the probability of them getting annoyed if we send them this marketing campaign and place us in spam? Or is the user's login attempt likely to be fraudulent? Or are they exhibiting some sort of anomalous behavior that might indicate that they could be a bot, right? So these don't sound like the kind of questions that you can ask a database, but really they are the kind of questions that in many cases a database should answer. The underlying pattern, the underlying patterns to answer these questions exist within your data. It's just that right now we think of machine learning models as something that's not really, or we think of, let's say, the complex equations needed to extract those patterns as something outside of the scope of databases. But this is really, if you think about it, kind of an arbitrary line, given that databases, at the end of the day, use logical operations in order to extract the data based on the queries you specify. So why not make those operations a bit more complex and add some extra power with machine learning into your database, right? All right. One second, I'm just trying to get back to the slides here. All right, perfect. So that's kind of what MindsDB does. And I should probably talk about like how it does it, at least broadly speaking. So MindsDB uses a SQL interface. And that's because developers are used to interacting with data via SQL. There's kind of two ways of interfacing with MindsDB. One of it is to integrate it with your database in such a way that you are essentially querying your main database, and some of those queries go through to MindsDB. This is supported in some, but not all databases. We support this in MariaDB and MySQL and ClickHouse, for example. And another way is to connect to MindsDB as though it were a MySQL database or a MariaDB database. Basically, any client that works with those, which really is most database clients, will also work with MindsDB. And in both of those cases, you do machine learning by essentially using insert queries to tell MindsDB what kind of questions it should be able to answer, and then using select queries to ask those questions and get a prediction as the answer. The way this happens under the cover is that MindsDB has a query planner, and it kind of figures out what part of the instructions are essentially instructions to get data from the database, what part of the instructions are instructions to create or use machine learning models, and then it joins that data from their database in the bits of the machine learning pipelines of the machine learning pipeline that actually require said data. So let's go through an example here to actually show you that this is not as complex as it may sound. So let's say that you want to predict what's a good price for selling or buying a used car. I don't know, you're a very large car collector or a dealership, and you have transactions, you have records of previous transactions. Now, let's say you can collect a bunch of those transactions that in hindsight you're happy about, that were quite profitable, that were quite good. And you can create a table out of those, which in this case we're calling training data. Now, I should mention here I'm using the second way of interfacing with MindsDB, where I'm treating it as a separate SQL database, which is connected to your main database, and you're kind of querying separately. The syntax for using it from within the database should be about the same. All right, so going back to the actual problem here, again, used car dealership, you have a bunch of transactions which you really like, and you want to use them as a guideline to tell your salespeople for how much they should sell cars in the future. So first you need to create a predictor, and you can see here the syntax. This is a bit new. This is not quite standard SQL. So you essentially tell it to create a predictor, you give it an identifier, a used car price, and you tell it where to train from. And this is essentially the source of the data. That select is going to get executed on your database, and you tell it what it should actually predict. In this case, it's price. Then you can use it to make single predictions. So You can tell it you want to predict the price for a car that has such and such model with such and such mileage that was built in this year, much like you would do where in a normal database in order to hopefully get a single record. Or you can do bulk predictions, which is, again, maybe a bit less intuitive if you've used databases, but there's often a situation where you don't want a single prediction, but rather you have a whole table with unknown data, and you want to make predictions for all of it. And the way we think about this is that this is essentially a join, where normally you would join extra data that's not in the table from another related table. But in this case, with MindsDB, you can join on a machine learning model, you can join on a predictive model, and augment the data in your table with some predictive insights. And you can see that in the last example here. All right, so I'm going to hand it over to Natasha again to talk about Lightwood, which is the thing that actually does all of the machine learning beneath these capabilities.
Great, thank you so much. So let's get into the meat of things, specifically how the ML framework works. So in the prior part of the talk, you just saw that we treat predictors as if they're AI tables, but how can you actually query results and what actually occurs as you feed data into these models? And so with that, we're going to be discussing Lightwood. Now, the goal of Lightwood is to create an encoder-mixer philosophy, and I'll walk you through what happens to your data as you build a machine learning predictor. First things first, we first do a type inference and a data pre-processing step. Again, in vein of the 3 automatable elements of what we want from a data science machine learning lifecycle pipeline. So in the first step, we first want to say for each column of your data set, what type of data are we working with? Is it numerical? Is it text? Sometimes even complex features like date time for time series or images. From that, we want to be able to then do a statistical analysis. And so Lightwood will then process each of the columns and get a rough estimate of what the distributions are. We want to promote responsible machine learning. So that means identifying the users of any aberrant information, for example, outliers or imbalanced classes that are going to be difficult to predict when we have a target of interest, which is the quality or the quantity that we want to predict in our data set. And then lastly, some preliminary data cleaning. So this could be, for example, how we treat unknown information and how we might want to process the features before we actually represent them as numerical vectors. In the next step, we'll talk about feature engineering, and this is what we represent as the encoder. Now, the encoder's job is to say, for a given data type, which is assigned to a column, how can we convert that raw data into something that is usable for a model to make then a predictive insight on? Feature engineering can come in 2 forms. It can be a rule-based approach, for example, normalizing numerical features, so they're of a very particular value that a model can understand with no extremities, or working with learned embeddings. So this means, for example, deploying powerful transformer models, which is how we represent our text information. So you get a vector that can then be used to train subsequent models. From that, we concatenate all of those features and we pass it to a mixer. And the mixer's job is the algorithm that actually predicts the target. Now, in the mixer, you deal with all of the ways you compile the model, which is to build its architecture, and also the details of how you train the model and any custom regimes that you might want. From those mixers, we'll then be able to have predictions, which are the output of interest. And you can, in fact, deploy multiple mixers to test the best algorithm for your data. Now, that's a lot of information, so I thought instead we could go through a high-level example of what's happening with Lightwood with an example with a Kaggle dataset. So in the following figure, you're looking at a snippet of a few rows within this dataset. Now, the goal of this problem is to be able to identify for the various customers and their profiles what segment of a marketing survey they're from. The internal team was able to identify whether you have an A, B, C, or D group. And in fact, what they're interested in looking at is to be able to then say, if we, for example, want to show ads, we want to be able to show the right ads to the right segment. So given all the other columns of information, can we predict what that segment target should be for a given customer? Now, from this data, you see there's a multitude of different types. You have binary information, for example, whether graduated or not. You have categorical information, for example, work experience, right, profession and whatnot. And then finally, you also have numerical columns, for example, the age of the customer. Now, all of these have to go through different processes, and I'll walk you through an example of what that might look like. Now, under the hood of the pipeline, let's see what each step does. First, we want to infer our types and clean our data. So for each column, Lightwood will take a small sample of data and make an estimate of what the most likely type should be. Now, this could be, for example, the spending score on the previous slide, which from first inspection is categorical. An example of 5 customers, you see that there are 3 different categories, low, average, and high, but there could also be an unknown category represented as a NaN. So dealing with all of those needs to be represented in feature engineering. For the second step, we want to be able to prepare those labels from the categorical information in a way that our model can then access. Of course, feeding text such as low, average, and high is not very easy for a model, so you can represent this as a one-hot encoded vector, which is quite the standard for categorical information. So in the following figure, we've now transformed this customer's profile into what could be a numerical representation a model can take. Now, in the following, each dimension represents whether it's unknown, low, medium, or high, depending on what they have. Now, this is just a small example of a single column. What Lightwood actually does is for every single column makes this sort of rule-based approach. And in fact, for example, we had an ID column, which we know has no information. Lightwood, as part of the cleaning process, will identify that to you and tell you that this is not an appropriate column to be able to then train a model. For the next and the last component of this, we want to then finally get to the point where we train the model. After we featurized all of our data, we have what's an input feature vector. And so for each customer or row in our data set, we have a representation in which we can train a model. These input feature vectors can go into a multitude of different algorithms. For example, we support neural networks or LightGBM. You can bring logistic regression, a very tried and true algorithm. And then Lightwood will then take an ensemble. So it will take every single one of these algorithms, process it in the way that's appropriate for them, and select the best model based on the validation performance to ensure that you have a model that's not only a good predictor, but robust across the different data that you have provided. However, let's take this a step further. We still think that users know their data best, and so they might want to introduce custom routines or custom pipelines. And so here I'll highlight how a user can potentially introduce their own individual strategies. For example, for a given data type, once Lightwood infers it, we can actually say, perhaps we want to change the cleaning process. So a user can introduce their own appropriate data pre-processing method per a particular column or per a particular data type. Next, a user might have their own approach for how they want to represent features for a data type. Now, in particular, this could be, for example, replacing the powerful transformers model with something that's easily more computable. For example, a bag of words. Or perhaps even changing the training paradigm of the transformer model, as indicated by custom encoder. You can include your own helper functions and whatever you need into the encoders, and then replace the way you represent the features. And then lastly, you can bring your own model architecture. If you have an idea as to how to test different custom training routines or the way you want to predict your target, it's as easy as being able to deploy your own custom model. However, the last component that I'll allude to is JSON AI. And in particular, we believe that if you want to introduce your own custom approaches, this shouldn't be as difficult as integrating with these complex pipelines as has been historically the case before. And so what we'll discuss soon, and George will lead you through this, is how we can auto-generate a JSON-like syntax that allows you to specify all the elements of your pipeline, from the features and the way they're represented, from the way you clean it, the outputs, and even down to the training and the testing split, among many other complex features as well. The only specification you need to work with this pipeline is to have the target, so you can customize what you need as well. And JSON AI will not only create you a free syntax, but the appropriate Python code that will be able to deploy your predictor of interest. And so with that, I'm going to pass it over to George, who will actually get to the meat of this JSON AI.
All right. So I'll make just a small note here, which is I see that there is a bunch of questions, and do keep asking those. Sorry we haven't answered yet, but the Q&A is at the end. Worry not, we'll get to those. All right, so Natasha basically told you about Lightwood, which essentially works by generating this code for machine learning pipelines, let's call them, from your data. But modifying this code directly can be cumbersome. And so is writing everything from scratch using the functionality provided by Lightwood. So we instead made this intermediary representation called JSON AI, which can be used to generate the actual machine learning code. And the way this works essentially is that inside this JSON AI, and you can see a quick example of it here, but inside this JSON AI, we define multiple steps, which we think are essentially everything you would potentially need in the machine learning pipeline. So things like cleaning your data, analyzing that data, splitting the data, featurizing the data using encoders, which can be something as simple as a numerical encoder that log normalizes things, or something as complex as a GPT-3 transformer that generates embeddings from text. Select training mixers, aka machine learning models, like GBM trees, neural networks, regressions, basically what Natasha was saying, and sampling those mixers, and then various steps for analyzing the model. And all of those will be present in that JSON AI, and they can be edited in either in the sense of, I want to change a small parameter here, or in the sense of wanting to replace a whole step with your custom code, which is as easy as just putting that custom code in a directory and modifying a string and that JSON AI to tell it, hey, use my custom module here. All right, so let me run you for an example. Maybe this will make it easier. So we are back to the previous CSV here with various information about the user, and including their segment for the purposes of, let's say, marketing. Right, so we can load that into a data frame, and we can create what we call a problem definition. And the simplest problem definition is just your target, the thing that you want to predict, which in this case is the segmentation for that user. And then you can call this simple Lightwood function called JSON AI from problem, which just takes your data and this problem definition, and it generates a JSON AI, as can be seen here in the top right of the slide. So in order to do this, it will try to infer types for your columns, and then we'll run a sort of statistical analysis to figure out various insights about the data. And based on that and your problem definition, it will try to generate a JSON AI, which best defines a machine learning pipeline that can hopefully solve your predictive problem. Once you have this JSON AI, you can call another function called code from JSON AI, which takes this and turns it into code, so actual plain text Python code. And then, because working with plain text code is a bit annoying, we have another helper function, predictor from code, which actually generates a predictor object from that code. And then you can quite easily call a learn method on that predictor, which will basically do all of those things, the pre-processing, the cleaning, the featurization, and the fitting of a model, and the analysis of a model. And then you can call predict on that predictor object to actually give it some new data and have it make prediction about the column that you want to infer. In this case, it would have been the segmentation column. All right, and adding a custom module, again, is fairly easy. So the only thing you need to do at the moment is to write a code that respects the interface of whatever module you're trying to replace. And all of these interfaces are fairly straightforward. Exact docs on that incoming, but it's as simple as having, like, for an encoder, a prepare method on how to prepare that encoder based on the existing data, and an encode method, which takes a data point and generates the encoder representation. So really, these are made so that you can include everything. And looking at this example here, let's say that you have a feature, an input column that is, which is a review, which is some text, think of review on Amazon, which can be quite complex, and you might want to handle it. Well, the way we would handle it is with a pre-trained language encoder, which is a pre-trained, let's say, BERT style model, which will generate some hopefully representative embeddings to be then used by our mixers. But let's say that you have a team of specialists working on text models or on review analysis, and they've produced something much better that generates embeddings, which you think are much more significant from your reviews, or maybe even sometimes generates the exact target that you need. All you have to do is to create this encoder based on your custom model, to put it in a directory, and then to modify this JSON AI to say, this column, instead of it being rich text that's handled by the pre-trained language encoder, it's rich text that's handled by my custom encoder, in this case called MLM encoder. And essentially, that's how you would go about modifying any sort of JSON AI. It obviously gets a bit more complex if you want to rewrite the whole thing, and it can be much easier if the only thing that you want to do is to change an argument in one of those modules. You can write these JSON AIs from scratch, or as shown, you can generate them from your data, and you can modify them. We do recommend this second approach because it's a bit easier, but both are available. And ultimately, what this translates to is not a black box, it's just Python code, and you can even just go ahead and modify that Python code directly if you want, although it's not quite as simple. All right, so I'm going to hand it back to Natasha to kind of summarize what we've talked about thus far and head into the Q&A.
Fantastic. And so to summarize what we've discussed today, first, George led you through what MindsDB is, and it's the way that we treat machine learning models as if they were virtual tables, and allows you to have a very natural interface with querying models as if they were data itself. Next, we talked a little bit about Lightwood, and this is specifically how we deploy custom ML modules or default ML modules. The three key elements that Lightwood really focuses on is the data pre-processing, preparing your data for a model to begin with, feature engineering, the way we represent that data into a form that a model can take, and then finally, the actual model building and training. And we've had much success integrating with other packages as well, so feel free to check it out. And then lastly, and stay tuned for this, JSON AI, which allows you to quickly edit aspects of your framework without needing to modify any massive code base. So this allows you the access to customize each individual components down to the feature level of how you want to treat cleaning, feature engineering, and even model building. Additionally, it allows you to access in a reproducible manner the elements of your framework that doesn't require you to change large code bases and even edit our defaults. Now with that, let's give you a little bit of a sneak preview of what's to come in the following weeks. In particular, we're going to have a debut of full documentation, every single function within Lightwood, how it works, and all of the details of what these inputs and outputs are. Now, customary to Lightwood is base abstractions for each of the cleaning, feature engineering, model building, analyzing, and even explain tools. And we'll show you with custom tutorials for each step of the process how you can deploy your pipeline in the way that you would like it to. And so with that, I would love to open up for questions. I see there's many in the chat, and so George and I will be available to be able to answer them. So we hope that you will join our mission. So with that, let me get to the questions then. George, are you here?
Yes, I am here and ready to answer any questions.
Great. So one of our first questions is what kind of complex data is supported? And I'm happy to answer that. So right now we handle not only text information with transformers, but to some extent images, but our real key hallmark is time series. We have many different time series features right now. Additionally, the ability to do anomaly detection. All right, the next question is, are there noticeable overhead computations when doing inference, or is the DB wrapper lightweight?
All right, so let me take this one. Basically, the database wrapper is quite lightweight in the sense of the transactional cost of actually getting the predictions into your database is very small. The computational overhead when doing inference really depends on the model. Usually with the kind of machine learning techniques that we use, it's not that big. but it depends. It can range from, let's say 10 milliseconds per prediction to 100 milliseconds for more complex types of data. And it's something that we are potentially working on optimizing, but thus far we haven't really noticed it to be an issue in all of the use cases we've had thus far. So sorry for not being able to give a more detailed answer there, but really the only answer is you really have to try it for your own data, and based on what that is, that depends. The overhead to actually train the models can be quite large for data sizes that are very large, or complex. So again, things like images and text. But that's usually a one-off thing, or at least a recurring thing, but recurring every day or every week. So you don't have to do it every time you need an inference.
Great. So the next question is, what packages are used to implement the modules and models? So most of our deep learning is done in PyTorch. All of us from the research side really like the flexibility of PyTorch, but we have integrated with other packages before. So for example, we've actually seen people use Optuna for hyperparameter tuning. Additionally, scikit-learn for different robustness metrics, for the simpler lightweight models like logistic regression or linear regression. George, do you have any other follow-up comments?
No. I think that pretty much covers it.
Great. I think to sort of tack on the next question here, how modular or low level can you be with this paradigm? Sort of ties in very nicely. The goal of Lightwood is to create these abstractions so that the inputs and the outputs are controllable, but what goes on under the hood should be as flexible as you need it to be. So we've created these abstractions, but you can do, for example, create your own helper functions and build whatever you need in there. So a test that we've done actually a couple of weeks ago was to build a masked language model. So the goal for text there is to say, if I have a sentence, I'm going to hide one of the words in the sentence and ask the model in a vast vocabulary, like 40,000 words, what's the most likely word that should have been there for that sentence? And we were able to deploy that no problem as our potential encoder strategy. We've also tried, I think, even more creative things. For example, if you have an encoder that's really robust and you don't need to build any model after that, the encoder already sort of operates as a model itself, you can inherit from that and then just deploy the model as if it were the feature engineering representation. So we've tried many creative things, but we're excited to see what the users can come up with as well. So the next question looks like an AI table stands for new OLAP databases generation. Can this be treated as multi-dimensional databases? And what happens if it is only right? So I am not familiar with OLAP databases, but I think they're dynamic. And if I were to answer this, I would say, so we handle streaming information, especially for our time series approaches. And to also clarify, the predictor sort of exists as a generator. So you can query it and get your data, but it won't automatically spit out data unless you ask it to. So if it's only right in that perspective, you don't have to call any of the information out of it. And you can save different models as necessary. George, do you have any further comments on that?
Not really, in part because OLAP is kind of a fairly broad term. We do interface with a lot of the BI tools and a lot of the, let's say, above database tools such as Snowflake that would be used in that paradigm. But yeah, I'm not exactly sure we can draw an apples to oranges comparison here. Also, I'm not 100% sure what you mean by only right. So yeah.
Yeah, so at the very end of the talk, feel free to ping us in our community channel where we can perhaps understand more and answer this a bit more in depth. So next question, let's see. Just got one here. Is it applicable to object detection problems? And any technique can be available for image processing in bounding box images? So that is a very interesting and creative question. As of now, since object detection is a much more complex problem, we don't have this out of the box, but we do have an image encoder, and we do have the ability to do supervised learning. meaning if you label for that, we will be able to predict it. That would be something that we're hoping to develop in the future. And George, feel free to jump in if you have any further thoughts on these things.
No, I think so. I think with bounding boxes, the answer there is pretty good, and I think one thing to keep in mind here is that in principle, MindSDB, as long as you have the supervised data to actually train, or the data trained this in a supervised way, MindSDB can really be used for a broad set of problems. So ultimately, a bounding box for an object is just a set of numerical coordinates, and we can predict numerical coordinates, and the input is just an image, and we take that as an input. That being said, will this be as good as architectures that have been handcrafted for 10 years for this specific problem? Probably not, because the aim of MindSDB really is first and foremost to tackle a wide range of problems, and it's likely going to work much better on, let's say, neglected problems where the state of the art hasn't been developed by teams of thousands of experts over the last 10 years. That being said, we do have some areas such as time series where we specialize in, where we are arguably on par with state of the art. But yeah, that's the question. So in principle, it could work. Probably will not be the best tool on the market for this just yet. But if you want it to be, you can always contribute to that. So yeah.
Another nice question was, how does MindSDB compare to other AutoML approaches? So we actually have an in-house benchmarking system because we also believe that reproducibility and robustness in our models is quite critical. We have, explanations and we have analyzers, but in particular, I can answer this in two ways. The first is we have an in-house benchmarking system, but the second is we have an external one, and that is specifically using OpenML's the vast swath of data sets to be able to see how well we do. So we're in the process of hopefully writing the paper soon, but right now, from what we can see, we're ranked somewhere in the second position right now for our AutoML approaches. But George actually extensively works with the benchmarking, so he's happy to, I guess, add any more for the internal work.
Yeah, so essentially the internal work is kind of currently just used in-house, and we don't have any official comparison with other frameworks and MindSDB on that. That being said, a lot of those datasets are actually public under MindSDB/benchmarks on GitHub. I think about 40 of them are. For a few others, we're kind of making the due diligence before releasing them. So we're fairly open with our performance on everything, and really one of our hopes is to be able to develop a very extensive suite of benchmarks for AutoML, in part because the existing ones are pretty focused on a very niche set of problems, and we want our benchmark suite to be focused on a much broader set of problems. And really the way we will be judging community contributions will be based on those benchmarks. We have a great focus on, we don't introduce new models because they're shiny. We introduce them because they improve results on our benchmarks. So they are a critical component of how we develop MindSDB, and they are something that we are very public with, and soon enough there will be easier ways to run it. Right now it's probably a bit annoying because it's not very well documented because it's internal, but the gist of it is that those are currently open, and soon enough they will be very easy to actually run for anyone to actually see if their changes to Lightwood are improving accuracy. So hopefully that about covers it.
Maybe to piggyback a little bit there. So a lot of conventional approaches focus on classification. We focus, since we're interested in supervised problems, on both classification and regression, a wide variety of different data types. So our goal is to really get predictors that are very robust across these different dimensions. All right, let's see. For time series problem, can it provide real-time anomaly detection? George, do you have an answer?
I believe the answer here is yes. Yes, that's actually one of the features we support and we are quite proud of.
Indeed, it's our time series expert's fantastic. So again, if you have any questions, feel free to ping us in the Slack that we will show you the link for very shortly. Let's see. Oh, if I train a model, what kind of maintenance is needed once being used?
So the maintenance that you need is really minimal unless your data changes a lot. So if your data is very homogeneous, if data from 2017 is representative of data from 2020, you can just train the model in 2017 and let it run. That being said, there are two types of maintenance that might come up, namely when you want to update the version of MindsDB and or Lightwood, which occasionally it might be a good thing to do because we keep improving it. You do need to retrain models, and there are some update functionalities that we are working on to make that very easy. I believe those are available in our public cloud. I'm not sure they're out in the open source version quite yet. And then you may want to actually, you might have a problem where your data is very unhomogeneous, where new data comes in each day, and it's very critical to update your model with it. For that, you need something like online training, which is something that's, well, let's say halfway there at this point. It is on our roadmap as a feature. It's not released to users just yet, but the way we plan to release it is it will make it fairly easy. So basically, you would just set a retraining frequency where you tell, if this much data has gathered in the backlog in the table used to train this predictor, or if this much time has passed, rerun the query used to train again to update this predictor. And during all of these updates, the models keep being live, so you don't have to worry about versioning and stuff like that. The updates are very seamless, and once the update is done, the model that's being used to predict just changes in the background. So there's no need there's no need to worry that the update, like while your model is updating, you will no longer be able to make predictions, have backup models and stuff like that.
All right, it looks like there's one question that we missed. How can I read more and get the slides? So you can download the slides, but this is a great segue into the last part of our talk, which is what the next steps are. So you can learn more about MindsDB on the website. We'll have a tutorial up for you on how to use JSON AI. I'll turn it over to George to finish up.
Yep. So basically, one of the core, I think, tenets of MindsDB and of Lightwood is that it's open source and it's community-based. And really, we have changed direction a lot, and we've improved a lot as a result of how people in the community have used this and based on the issues that they raised and the kind of problems they had. So we really want to ask you that if you like this, you should actually go to GitHub and try it out and figure out if it fits your use case. And if it doesn't, well, this is not a black box. You can actually make a PR to make it better for you. Or you can make an issue and you can tell us with whatever degree of details you want why it's not working for your use case or what you think we can improve. If the documentation is not suitable, in your opinion, if it doesn't explain something well, again, like you can make an issue, you can ping us in our community Slack. So really, we are hoping to make this a community effort where we are giving out this great tool for free with all the source code, with all the code open source. And hopefully our community can, in this process, tell us what they actually want to see, how they actually want to transform this tool. And you can actually be part of this growing because right now we are in this spot where I think we are pretty, let's say, big in the AutoML market, but the AutoML niche is something that's still growing. It's something that most people still haven't heard of. So I'm really hoping that we can build a community and you can be part of a community that brings this product to the forefront of what it means to do machine learning. Because ultimately, this is, I think, an obvious next step in the evolution of how this should be integrated in most companies and in most products. So that tidbit aside, you should probably go to GitHub, github.com/mindsdb/mindsdb for the main repository for MindsDB itself, and github.com/mindsdb/lightwood for Lightwood if you're more in the nitty-gritty, in the engineering, in the research side of things. And you should go to mindsdbcommunity.slack.com to actually join our community Slack. It's free. Anyone can ask questions. You will find me and Natasha and a dozen other of our team members there. And you can definitely install both MinesDB and Lightwood locally. It's as easy as just doing pip install MinesDB or pip install Lightwood or docker pool MinesDB/MinesDB if you prefer Docker image. But if for some reason you don't want to try this locally, maybe you don't have the resources or maybe you don't want to bother, we also offer a fully managed version of MinesDB at cloud.minesdb.com. So you can also check that out. That's about it. I think I've shelled out all the relevant links here, and I'm looking forward to see how you guys mess with this. And again, stay tuned for the Lightwood documentation. Feel free to dig in the repository in the meanwhile if you want, but just keep in mind that it's still a bit untidy. So that will be more presentable soon. Thanks a lot for your time.
Indeed. So the Lightwood README for our GitHub will have different updates as to when the documentation is live and when the tutorials are live. But in the meanwhile, if you ping us on the Slack, even with questions that we might not have answered in this talk, we're happy to engage with you and answer these in depth. One of the research team is almost always answering the Slack questions, so we'll be excited to hear from you. Thank you so much.